Yes, I stopped. Then you need me marking the person. Yeah. Yeah, they people come to come learn everything. Like they do like so you do everything. You like rethought or because like it's hard to do everything.
Yeah, that would be nice.
Especially on like Christmas, we're like we have to do other stuff. I got to go to
All right, shall we get started? So I think we ended up last time, I asked you to just make sure you could do all those trig integrals from 6.2 and to not start any of the ones with the trig sub, right? I felt like, you know what, go get the other stuff done, and we're going to do more of this today. So let's pick up where we left off. We're talking about if we were doing, yes?
Sorry, I was going to say, on the homework, I got to see the problems where, like, just before this, we had the power reducing formula.
Uh-huh.
So, were we going to be, like, using that, or like, did we cover enough of that? Well, I think we did.
Power reduce. Well, I mean, I'm pretty sure I did at least one problem where we had to use power reducing. I think I did like cosine to the fourth power or sine to the fourth power. We had to do power reducing, I think, twice in that example.
I just didn't know, like, if there was anything, because I kind of forgot.
Yeah. It'll happen in these problems as well. It may show up.
Oh.
Yeah. Uh-huh.
Can I write those down on the, I know we can print off separately,
Yeah, you can have that other sheet. That's it, though.
but don't write it down.
Yeah, not on there. Yeah. All right, so I think today we'll actually do a problem where we have to do power reducing. So we'll see it. We'll see that in there. We'll see the power reducing. And if you're still unsure about it, just come by my office. We can do something. All right. So what we did last time is we said if we ever are trying to do an integral where we see the square root of a squared minus x squared, that we're going to make this. Sorry, right here. Square root of a squared minus x squared. That we're going to make this trigonometric substitution. X is equal to a sine theta. And I think I did like one example of that at least. I'm going to move on now to the other two examples or the other two situations we can run into, and I actually listed them backwards here from the way they are there. But if we ever see the square root of x squared minus a squared, we will make the trig sub of a secant theta. And if we ever see x squared plus a squared, or you can flip these around, a squared plus x squared, then we'll make the trig sub a, x is a tan theta. So I think the best way to see this play out is to do examples, all right? So I'm going to start one out here. I want to start with one that uses this second method. So let's do the antiderivative of 1 over, let's go x squared square root of x squared minus 25 dx. Right, so take a look at this, and again, this is where we have to go through that whole procedure of like, do we know how to do this? Is this just a basic U sub, integration by parts? Well, I see that I have a square root of a variable squared minus some constant squared. So this is looking a lot like this second case, right? So I'm going to make this substitution right now. What's a for us here? 5. Everyone see that it's 5? Yes?
Yeah.
So a is 5 here. So I'm going to make the trig sub right now. The trig sub I'm making is I'm replacing x with 5 and then secant theta, right? That's the trig sub. 5 secant theta. The next thing that I do normally in my procedure is I differentiate this now. So I take the derivative of this on both sides. I get dx is 5. 5 comes for the ride. Derivative of secant theta is secant theta, tangent theta, d theta. All right, that's just normally the way I do it. I make the trig sub, then I do the differentiation. Then the next thing I'm going to do is I'm going to figure out what is the square root of x squared minus 25. The thing that kind of triggered me to do this whole thing, right? What does that turn into? So I'm going to just rewrite it. And I'm going to replace x with 5 secant theta. That becomes 25 secant squared theta. Right, that's what would happen if I took that x right there and squared it, right? It would become that. And then I still have minus 25. And both of those have a 25 in them, so I can factor 25 out. And when I do that, I get like the whole reason we're doing this. And that is this right here is a Pythagorean identity. What is secant squared theta minus 1? Tangent squared theta. Tangent squared theta. So this becomes square root of 25 tangent squared theta. And then you take square root of each one, you get 5 tangent theta. That's it. Hey, just be careful with the camera there.
Yeah.
All right. 5 tan theta, right? Any questions on this? We saw this. That told us to do this. We put the substitution, we differentiate it, and then we go figure out what that square root turns into. And now what we're going to do is rewrite the entire integral in terms of theta instead of in terms of x. So I come over here. Okay, here we go. 1 over. All right, x squared. Right, x squared. Well, x squared, remember x is this, right? X is that. So that squared would be 25 secant squared theta. 25 secant squared theta. I'll just color code this. This right here, right, is that. Okay, I've replaced the x squared. Now I have to replace the square root thing, right, on the bottom, this square root. But that square root gets replaced with this, right? Because that's what that square root turns into. So that's times 5 tan theta. Am I done? I have to replace the dx, right? I have to, and this is the part students forget. I have to replace dx with that whole thing. Everything gets replaced. I'm going to try and squeeze that in here, right here. Just make sure you understand this is separate. Right, so when I squeeze that in there, I'm going to get a 5 secant theta, tangent theta, d theta. And if you look at this, we now have a trig integral, right? It's no longer this square root stuff, it's a trig integral. And so hopefully I can do this trig integral. And I'm seeing a lot of things good happen here. Do you all see all this? Like I get a 5 here, gone. I get a tangent theta gone. One of these secants goes away, right? Just one of them. So I believe when I'm done here equals integral, let me see. I have a 1 over 25 still, don't I? So I'm going to put that out front. Equals 1 over 25. Okay, so that constant's out. And then the only thing left was a secant on the bottom, right? That's the only thing left. The secant on the bottom, which is really cosine. 1 over secant is cosine. I'm going to write it down just so 1 over secant theta, d theta is where I am. But that's just 1 over 25 integral of cosine theta, just by definition. And that integral is really not an issue, hopefully, right? Antiderivative of cosine is sine, so 1/25 sine, what? Sine theta, d theta plus c. I'm sorry, not d theta, plus c. Sine theta plus c, right? That's my antiderivative. Questions? We're not done, but any questions up to this point? Everyone good with where everything came from? Question? You look like you have a question. Just following? Yes?
Just near the part before, how do you get 25?
X squared, square this,
Okay.
right? So you have to square the 5 and the secant. Yes? This right here, this comes from this identity. One of the this is a Pythagorean identity. You can replace the x with theta or anything you want. All you do here is just subtract 1 on both sides. If I subtract 1, it goes away. And then I have that secant squared x minus 1 is tangent squared x. Secant squared theta minus 1 is tangent squared theta. So that's what I'm using here. And then square root of each one, so that becomes 5, and the square root of something squared just goes away.
And then you took it over to that side?
Well, that's what this is, right? When I see this, that's what it turns into. So in my integral, that thing right there is going to get replaced with the 5 tan theta. So that's right here.
Right. So the 25 secret.
That's this. That's this thing squared. You see it? So every piece has to be replaced. Every piece.
It's not just one.
Oh, no, everything we see here. Had this been x cubed, then we would have had to have done that cubed, right? And then we'd have 125 secant cubed theta there. Any other questions? Because we're not done, right? Our answer is in terms of theta, our answer needs to be in terms of x. So the way to get back to figure out, we need to figure out what sine theta is in terms of x. I said last class that where you go to get this information is right here. Go to your original trigonometric substitution and create a reference triangle off that. So I'm going to do that drawing right here. The drawing I have is going to come off that equation. So first let me take that equation, let me divide both sides by 5. And the reason I'm doing that is because all of our trig functions are ratios on a triangle, right? So I'm creating the ratio on the left-hand side. I'm going to draw my right triangle. I'm going to label my angle theta. And secant, by definition, is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant should be hypotenuse over adjacent. So this should be my hypotenuse, and that should be my adjacent side. Follow? So I'm going to draw this hypotenuse adjacent. And you can double check it, right? Cosine would be 5 over x. Secant would be x over 5. So that matches. And we are interested in what? Sine. Okay, sine is opposite over hypotenuse. So I need this opposite side. But since I have two sides of a right triangle, I can always solve for the third side. For this problem, because it's been a whole week since we've done this, I'll actually solve for that side. I'll call it b. We know by Pythagorean that 5 squared plus b squared is x squared. And I'm trying to solve for b here. So I will take the 5 squared to the other side. Right? Yes? And then take square root. So b is square root of x squared minus 25. We good? Yes, secant? Yeah, okay. Yeah, it's the same thing here.
Is that just a convenience, or was that supposed to?
Somewhere on your right triangle, you're going to see something that's going to look like the square root thing that you originally were like triggered everything to happen.
So can we use that kind of way, like, oh, we know we're on the right path?
Yes, but there's sometimes that it's not going to look exactly the same. So I don't want to say always. I don't want you to get alarmed if it looks a little different. But most of the time it does show up. So I wouldn't be alarmed to see it.
And do we typically always have to, like, draw, like, whenever we get one of these problems where we're subject to the A sign?
Yeah.
We're typically going to have a reference triangle.
You're typically going to have it. Sometimes you can get it or get around it depending on what you know here. But in this particular problem, I think the reference triangle will get you out of every bind that you're in. Sometimes there's ways around it, but that would be a special case. So the reference triangle is kind of like you always default to that. All right. All right, we're ready for an answer, right? The answer to this question is, so final, yes? X over 5. Well, that was the original trigonometric substitution that I made, right? So if I asked you to solve for secant theta, get it by itself, you just divide both sides by 5. So what I'm doing is I'm trying to write secant theta by itself so I can look at secant theta as a ratio. So I got that 5 out of there. If this 5 wasn't here, then over here what I would do is I would imagine that that's a 1 down there. And then my ratio, this would be x, that would be 1. Yeah, no problem. All right, so we have 1 over 25, right? And then sine theta off of my triangle. I never put this side here. This side was square root of x squared minus 25, right? So sine would be that opposite side, this, over x squared, right? Plus c, box it up. That's my answer. Yep.
Is it just coincidence that it turns out as the formula?
Well, that's what we were just saying, I think, right? Are you talking?
I'm sorry, I was focusing on the other stuff.
What? What are you talking about? Is it a coincidence that this is here?
No, that's in the same format as secant over there. The x squared minus a squared is x squared minus a.
Is it a coincidence that this is x squared minus a squared?
That fits that formula on the left.
Well, that's,
Just a coincidence, right?
I'm not sure what you mean. We started this problem because we saw that in the problem, right?
Yes.
So is it a coincidence that we're seeing it where here?
It happens to be b.
Not really. We should expect our triangle to reflect this relationship.
Always.
Always. But sometimes, I think there was a question, will it always look exactly like that? Sometimes it'll be off a little bit by a number. It depends on the problem, because just stay tuned. You'll see there will be some problems where it may not exactly be the same. Yes?
So on the final answer, how did we get the x squared in the denominator rather than just x?
We want to know what sine theta is, right? Oh, I don't know why I put x squared. Yeah, I apologize. Yeah, I don't know. I don't know why I did that. This over this, right? Okay, thank you for pointing that out. That's our antiderivative.
I have a question.
Yes?
Do we have to write sine in the actual answer?
Here? Here, no, sine's not here. We're replacing sine theta with what it's equivalent to in terms of x, right? So you're replacing this expression, sine theta, with what it is based off of this. See, look at this triangle. If I ask you right now, what's sine of theta, what are you going to tell me? Opposite over hypotenuse, right? That's what sine theta becomes.
So like on a test, can we just put sine of secant of x over 5?
Can you do what?
On a test, can we put sine of inverse secant of x over 5?
I know what you're saying. I mean, I understand what you're saying. If you want to do that, I'm okay with that.
So we don't need to like solve all the way.
Well, if it's in terms of, your answer will be in terms of x, right?
Right.
So that would be okay with me. But I don't teach it that way because I want my students to be comfortable with the idea of going to a reference triangle. I think that that's a skill that's helpful for a student. But if you are okay with that, you've seen that way before, you can do with that. But I'm not going to tell everyone to do that.
Okay.
I will accept that because it's technically right, right? Most textbooks will not do that, okay? Most textbooks won't do that because you've got an inverse trig inside of a trig, and then differentiation of that's messy, so it'll most likely be like this. So hey, let's check our answer. How do we check our answer? Differentiate that, right? So I'm going to take a quick derivative of this. First, I'm going to ignore the 1 over 25. That's just going to come for the ride. Okay, now I'm going to do derivative of this, which is going to be quotient rule. So I'm going to do derivative of the top first. So the derivative of the top is, well, derivative square root of something is 1 over 2 square roots of that something times the derivative of what's inside of here, which is 2x, times the bottom function, minus the derivative of the bottom function, which is 1, times the top, which is square root of x squared minus 25. All of this over the bottom squared, right? That's where we are. All right, 2 cancels, 2 and cancels. Okay, so now I have, let's see, what do I have? 1 over 25 in front times these together, that's x squared over the square root of x squared minus 25, minus, then this is just square root of x squared minus 25, and then all of this is over x squared, right? And now to put these two together, I get a common denominator. So I treat this like it's over 1. And I'm going to put these two together, so I have to multiply the top and bottom of this by root x squared minus 25. So when I do that, I get this fraction, x squared over square root of x squared minus 25, minus, when I put those, multiply the root on top and bottom, the root goes away on top, so I get x squared minus 25 on top. On the bottom, the square root of x squared minus 25. And now I can combine those so long as I distribute the negative through. So I have now 1 over 25 times x squared minus x squared plus 25, right? Negative, negative, and negative is positive. All over square root of, this is the common denominator, and then all of that over x squared. What does that numerator become? 25, right? What? 1. So I get 1 over the square root of x squared minus 25, all of this over x squared, right? But then that's the same as that over 1, and then you can flip it up, and when you flip it up, it comes that, and then that was the original problem. So it works. It works, right? Okay, let's do another one. How about this one? All right, so I look at that and I say, all right, hey, which of these three does that look like? First, second, or third? Third one, right? With A being what? 3, right? Do you all see that? We've got x squared plus a number squared. Here, we're going to use this trig sub with A being 3. Everyone see it? Okay. I'm trying to give myself a little more room here. Let me do it over here. So my trig sub is going to be x is equal to 3 tan theta, right? Then the derivative of that is 3 secant squared theta. Don't forget to put d theta at the end of that, right? Because you've taken the derivative. Y'all understand what I'm doing here is doing the derivative with respect to theta on both sides? So left side is actually dx over d theta, and then I just multiply both sides by d theta. All right, continue. All right, I've got to figure out what the square root of x squared plus 9 is. See, I'm just going to go look to see what this ugly root turns into, because that's what the trig sub is based upon, right? So to do that, I replace x with 3 tan theta. So it would become what here? If I square this, what do I get? 9 tangent squared theta, then plus 9, right? I can pull a 9 out of these.
Yeah.
And this is the Pythagorean identity, right?
I'm really confused where you got the other.
Right here, plus 9. So right when we square the x, that's this thing squared, that's this, right? Square that, you get 9. Square that, you get tan squared. And then you have plus 9. I'm just rewriting this, right? Just rewriting this here. Is that okay? All right, this becomes what? Secant squared theta. And now we can take square root of each one, because we no longer have plus or minus, we have multiplication. So this becomes 3 secant theta. Question? What's up? Pythagorean?
The identity, I was thinking, wasn't it a negative secant theta? But I think I might
The identity we have,
get the sign wrong.
yeah, the identity we have, I'll do theta. Tangent squared theta plus 1 equals secant squared theta. Right? So if you have secant squared, you replace it with tangent squared theta plus 1. But if you have tangent squared, you have to move that 1 over. Right?
Yeah, I just had the sign wrong.
Yeah. But that's like the master formula we're using for this step from here to here.
So you change it to secant squared just so you'll have one thing that you can reduce to get it out of the root, right?
I'm doing it because if you take, right here we have 2 terms, don't we? So if I have like the square root of a plus b, that is not the square root of a plus the square root of b. I'm not allowed to do that with addition, right? So what I'm doing is I'm manipulating this to get it to be a product.
Okay.
And if I make it a product, then I can do the square root of each one. That property is okay, right? So this is all right. If you do square root of a times b, that is the square root of a times the square root of b. That property is legitimate. So I've turned the sum into a product, and now I can do the square root of each one, and now I've got nice little expression. Okay? All right, I'm ready to rewrite everything now. So I'm going to come back over here, change markers. Integral. All right, 1 over. All right, we happen to have an x squared down here again, right? X squared. So what will x squared be for us? 9 tangent squared theta, right? That's our, so that bottom piece right here, x squared, is 9 tangent squared theta. All right, that is just that right there. Now I need to replace the square root on the bottom, but we already figured out that that square root is equal to that, right? So that's going to become 3 secant theta on the bottom next to it. And do not forget the very important dx, right? The dx must be replaced with dx, and we know dx is this, right? 3 secant squared theta d theta. That's the red part. It's the green part. Everyone see where all those pieces come from? Are there any questions?
I just noticed before, when we've been doing subs before, we were trying to get like dx with theta to look like something we already.
We're not doing any of that.
Yeah.
Yeah.
So now we're actually like putting something to it.
This method, what we're doing is we're taking something really hard. We're making a substitution that doesn't seem like it's going to help us because we're actually replacing something simple with something complicated. But the way we've designed it, the way we've picked things, is that when we're done, we're going to get a trig integral. And we're hoping that we can handle this trig integral. Right? There's no guarantee that we can do this, but there's at least now it's a trig integral.
Got it. Okay, that's cool.
So let's see what happens now. I mean, there's nothing that says this is going to go easily. I see the 3's cancel, right? I also see a secant can go, right? So this secant can go from that one. I've got 1 secant gone there. And that's all I can cancel out, right? Or reduce. Let's pull out a 1/9. That 9 on the bottom, just pull out as 1/9. I've got secant theta left on top. That's that. On the bottom, I have tangent theta. Tangent squared theta d theta. And that's where I am. Yes, question?
Yeah, I was gonna ask, like, on that one, it would be a lot easier to substitute tangent squared theta with secant squared theta -1, or everything on the sine and cosine?
At this point, it's whatever you want to try. So if you want, we can go down that road if you want to. But let's all recognize that right now, the way this sits, I mean, we got to figure, we're not done, right? We got to figure this out, right? This is not a basic U sub. Think about it, like, is this a U sub? If you let U be secant, what's the derivative of secant? Secant tangent, well, it doesn't matter. It would have to be in the bottom anyway, so that's not going to work. If I let U be tangent, what's the derivative of tangent? Secant squared, I don't have a secant squared, right? So it doesn't look like a basic U sub's going to work. So we got to try something else. One suggestion being made here is, could we replace the tangent squared with, move that over, secant squared -1? Could we?
Yeah.
Okay, would y'all like me to?
No.
No? But why not? Why not? No, don't do it, please.
You would get 1 over secant theta times secant theta.
Let me write what we would get. If we use the Pythagorean identity, okay, let me write what we would get. If we replace tangent squared with this, secant squared theta -1 d theta. The bad thing here is we cannot split that into 2 fractions, right? If it were the other way around, we could.
So sine and cosine?
So I think the best approach here is to go and turn this into sines and cosines. So turn your secant into 1 over cosine and turn your tangent squared into sine squared over cosine squared. When all else fails, go to sine and cosine and cross your fingers, right? And hope for the best. So do y'all see what we're saying here? Like this can't split into 2. Like if it were the other way around, it would, and I'd probably go down that road. But I'm going to make the decision here upon the suggestion of some of you in the class to replace secant with 1 over cosine and tangent squared with sine squared theta over cosine squared theta. That's just the definition of each of those, right? That's what secant is. And on the bottom, that's what tangent squared is. And now I'm going to do that thing where you flip the fraction up. And so when I flip that up...
How do you do the fraction flipping up again? I know it's basic algebra.
Well, no, I mean, I'll go back to this. If you take 1 over cosine theta, and I'm going to go back to old school notation. We're dividing that, right? We're dividing that by sine squared theta over cosine squared theta. That is the same as, now this is what you have to remember from old school algebra, is that division is the same as multiplication of the reciprocal. So that division turns into multiplication, but instead of doing that, you reciprocate it, so you flip it over like that. So that expression is the same as this expression. And then things can start to cancel. Cancel. I got in trouble at a math meeting the other day because I said cancel. Y'all know technically it's not canceling, it's called reducing, all right? But most students learn canceling, all right? But the technical term for making terms do that and become a 1 is called reducing the fraction. Just like if you take 4 over 8, you reduce that fraction to 1/2, right? But if you had 4 over 4, you would reduce that fraction to 1. But for some reason, back in lower level, when you're learning it in grade school, whatever it is, high school, they say, oh, you cancel the 4s.
I thought it was a joke about canceling on social
Yeah,
media.
no. Yeah, so, I'm going to continue to say cancel because that's what most people say, but like if you're a math major, just understand, or if you're going to, technically it's called reducing. I don't think it's going to change our ability to do a problem, right? We're still going to be able to do it or not do it. Reducing, we get cosine theta over sine squared theta. Nothing else reduces. U sub, basic U sub. U would be sine, the derivative of that would be cosine. It's all right here. So I'm going to do a basic U sub now.
You also write it as cotangent, cosecant.
And just goes,
Take the derivative.